Again, in this video, we're going to go over the most important theorem in calculus, which is known as the fundamental theorem of calculus. Now, the fundamental theorem of calculus has two parts to it. So in this video, we're going to go over the first part, and then we'll go over the second part in another video. Okay, so here's what the first part of the fundamental theorem of calculus says. If f is continuous on a closed interval from a to b, then the area function, which is given by this definite integral, is also continuous on the closed interval from a to b, and it's differentiable on the open interval from a to b. In addition to that, if we take the derivative of the area function, then we get the function evaluated at x. And that basically means that the area function of f, which is this definite integral, is an antiderivative of f on the closed interval from a to b. That's because when you take the derivative of this area function, you get f of x back. And so that means this function right here, which we can think of as capital F of x, must be an antiderivative of small f of x. Another way to think about this is, in a nutshell, what this is telling us is that the derivative operator and the definite integral are inverse operations of each other. So when you take the derivative of this definite integral, they cancel out. It leaves you with the original function, but notice the function depends on x. So you get f of x back. And that's because t is a dummy variable, right? The variable of integration for a definite integral is a dummy variable. This definite integral actually depends on x. Okay, so let me show you an example where we use this. So let's suppose you wanted to find the derivative of this function, of this definite integral. Now, first of all, technically this is not an area function, so we can't apply the fundamental theorem of calculus. And the reason it's not an area function is because when you have an area function, lower limit here needs to be a fixed number, then the upper limit needs to be a variable. Okay, but we can switch these. We have a property that says we can switch these, and when we switch the upper and lower limit on a definite integral, we just have to put a minus sign in front of the definite integral. So let's do that first. So let's switch the upper and lower limit and then put a minus sign in front of the definite integral. Okay, so those are equal, and then we'll take the derivative of this. Now, of course, we can pull this minus sign out of the derivative operator since it's a constant. Now we do have an area function here. And the fundamental theorem of calculus tells us that the derivative of an area function gives us this function inside here, the integrand, but it's a function of x, it's not of t. So the original function we had here for this area function was f of t is equal to this square root. Okay, and so the fundamental theorem of calculus tells us that we're going to get f of x if we take the derivative of this area function with respect to x. Of course, there's going to be this minus sign that's in front of it. Okay, and of course, f of x would simply be this square root with an x substituted in for the t. Okay, so you get negative of this square root of x squared plus 1. So what's nice about this is there's no need for us to evaluate this definite integral because we're just going to turn around and take the derivative of it. And these are really inverse operations of each other, and so they're going to cancel out. Now, if you did do that, right, if you did find the definite integral and then take the derivative of it, then you would end up with the square root of x squared plus 1. Okay, so rather than having to go through all those steps, right, of actually taking the definite integral and then turning around and taking the derivative of it, by the fundamental theorem of calculus part 1, we know these are inverse operations. And so they just cancel out, and we're going to end up with the original function but as a function of this upper limit. Okay, so let's look at another example. Okay, let's find the derivative of this definite integral. Notice technically we can't apply the fundamental theorem of calculus to this because this is not really the way we write an area function. So in order to use the fundamental theorem of calculus, this definite integral must be an area function. Okay, so here's how we're going to fix this. We're going to let u be this upper limit. And if we do that, then we're going to take the derivative with respect to x of this definite integral that goes from 0 to u now. Okay, and just to make things a little bit easier, I'm going to call this definite integral y. Okay, and so then we're really just taking the derivative of y with respect to x. Now, the issue that we're going to run into, though, is notice that this is now an area function, okay, because this upper limit is now just a variable, right? It's equal to u instead of like x squared. This is an area function that depends on u, right? This is depends on this upper limit. And we're wanting to take the derivative of it with respect to x. Okay, in order to do that, we're going to have to use the chain rule. So we can find dy dx, but in order to find it, we need to first find the derivative of y with respect to u, and that's because this y right here, right, look at this, this is really depending on u, right? This is an area function that depends on u. And then if we multiply that by du dx, and you can see that u does depend on x, right? So we should be able to find that derivative as well. When we multiply those together by the chain rule, we can get dy dx, which is what we want. Okay, so let's do it using the chain rule. So what's dy du? Well, that's essentially the derivative of this area function with respect to u. Okay, and so here we can apply the fundamental theorem of calculus because we're taking the derivative of an area function with respect to u, and the upper limit here on this area function is u, right? This depends on u. Okay, and so the fundamental theorem of calculus tells us that we're going to end up with cosine squared of u. Okay, so that's our dy du. And then, of course, du dx, the derivative of this with respect to x is just 2x, right, using the power rule. Okay, so we have dy du and then du dx. Let's just multiply those together. So we get cosine squared of u times 2x. And then let's go ahead and replace this u. We know u is equal to x squared, so this is going to be cosine squared of x squared times 2x, and I'm just going to put the 2x in front. Okay, so that's how you would find the derivative of this definite integral. So I think you can see that the fundamental theorem of calculus part 1 is very useful anytime you take the derivative of a definite integral. Even if this definite integral is not an area function, you can always manipulate it to be an area function by letting this upper limit, like using substitution, right, for this upper limit and calling it something like u, like I did in this case. And then you'll have to use the chain rule to find the derivative of this function with respect to x, right? You'll have to find it by using the chain rule, dy du and then times du dx. Okay, I hope you found this video helpful. Thank you for watching.